thank you very much for all of you who stayed here in this, long afternoon. And of course, I want to say happy birthday to the birthday boys. Two of them are still there here, so that's nice. And actually, I remember reading a joint paper of yours. It's about Erdős type problems when you had a restriction of how many points you have inside. Yes, you remember, or yeah, briefly. Yeah, it seems that you do. And high school exercise. So continuing that high school exercise with Jussi Károly, we had papers going further, or I don't know, maybe high school 1, 2, 3. So I'm going to talk about some beautiful problems. Most of them somehow originate from Erdős, although the variants might have, I will state who to blame for asking such questions. And I'm going to talk about distinct distances. And in these days, when we say distinct distances, then many of you know that there is this breakthrough result, in the last 5 years, I should say, by Guth and Katz, but this is not quite what I'm going to talk about. Distinct distances under various conditions. And all the questions or all the problems, I'm going to mention 3 problems, at least. And they have the common feature that you can translate the problem into point curve incidences on Cartesian products. And at the end, I will show you a general framework understanding polynomials, which are non-expanders. I will tell you the definitions and how to deal with them. And then you have a kind of general tool which works to many similar problems. And so let me begin with the problem. This is distinct distances from 3 points. So distinct distances. And first, so this is our first, from 3 points on the plane. And this is a question which was asked by Erdős, Lovász, and Vesztergombi. And as all the problems I'm going to mention, this is still widely open. So as the title says, you have 3 points somehow and n points. So 2 point sets, one contains 3 points and an n and some other points. And the question is that you check the distance from the points. For every point, you check all 3 distances. And then you collect this distance set, the set of distances which you will see from any of those points to the set there. And the question is how large it should be. And the conjecture is the conjecture that it should be around linear in n. Now, this conjecture, as it's stated, was refuted by Elekes, and this conjecture is false if the 3 points are collinear. If you allow the 3 points to be on one line, then, you can try. This is 0, this is +1, and this is -1. Now it's a high school exercise from this point to find a point set where the number of distinct distances is just around root n, not more. But there was a beautiful result which implied, among other things, so this was a result of Elekes and Szabó, and SOBO, that if the 3 points, if no collinear, I mean the 3 points, if ABC are not collinear, then at least you have the number of distinct distances is at least the distances is at least n to the 1/2, that would be square root, plus delta. It's a small delta, you barely see it. That was not explicitly calculated. It just shows that there is a jump. So for collinearity, you have root n, but if you forbid the 3 points to be collinear, then suddenly you have much more than root n. Still, the conjecture is that this is n. Now, using the method, which hopefully at the end I will tell you how to use incidence bounds on Cartesian products with Micha Sharir, we prove the lower bound, which is it's about n to the 6/11. So it's larger than 1/2, at least with 1/11. So delta is at least 1/11, and this is the best known bound. We published it in 2015. So it's a relatively recent result, and it's not clear. We don't have any construction which is subquadratic, sublinear, so much less than n. But this is the best what we can show. But this exponent follows from a general improvement we found following the footsteps of Elekes and Szabó. I will talk about it, but before that, let me introduce the second problem, and then the third one. Distinct distances, but now, so maybe I just write here n to the 6/11, the best known bound. The distinct distances, the title, between two lines. Well, two lines, that's just silly. Two sets, point sets from two lines. So you have one point set, P1, along one line, this is line 1, and another line, line 2. There you have another point set, P2. What is the minimum number of distinct distances if you have? For the sake of simplicity, let us suppose that the two sets have the same cardinality, which is n, then the number of distinct distances. So there are two special cases. So I want to say that the number of distinct distances is always at least, well, n squared would be, or something close to quadratic. That would be a good conjecture. But, well, at least I want to say something. But before I say anything which is larger than linear, you clearly have at least n distinct distances. You just choose an arbitrary point and you see all the others, you have n. But, well, you can't really put them together nicely to have a small distance set unless you have, say, two parallel lines and, say, from 1 to, you just see you have a nice arithmetic progression up to n, say. Then you can check here the distance between any point here to any point there. Depends only on the difference of the of the numbers. So this is one accident when the number of distinct distances is about n, not more, right? And there's another one when two lines are orthogonal. How? Well, just write 1, root 2, root 3. So square root of I here and square root of, well, also the roots of the integers here. And between any two, the distance is just, well, It's a square root of the sum of squares, which will be again an arithmetic progression. So here again, the number of distinct distances is n. But if you forbid the orthogonal and parallel case, then suddenly there is a jump. And it was conjectured by Purdy. And first improvement, as before, is, this is slightly different. So I will talk about Elekes Szoba, and in this case, it's Elekes Ronyai. They proved that, well, at least the number of distinct distances between P1 and P2, they have the same size n, is larger or equal than n to the 1 plus delta, with some delta which was not explicitly calculated. But again, there is a jump. So there are two cases when the number of distinct distances is small, but suddenly if you forbid this very special case and your alpha is somewhere between 90 and 0, then suddenly there is a jump. There is this, the best bound is due to Schaffer, Schaffer, and myself, and that the magnitude is the number of distinct distances is always at least these distinct distances, or let me use this one, is at least some c times 4/3, n to the 4/3. Now this result since then was extended. The same holds not only for two lines. There is nothing really special about the two lines other than the product of the two lines will give you a low degree polynomial. So extensions with the same exponent, it's Pach and the Zoo. They prove that if you have two irreducible curves and you see the distances between them, then, well, if none of them are line or circle, you can actually have two circles with a small set of distinct distances, like with the arithmetic progression, then the number of distinct distances is at least n to the 4/3. And there is a recent extension even in higher dimension, that's by Oritras. Now, I will show you a third example, and then I will either show you how to get curves out of those problems, or maybe if I'm out of time, then I will just give you a general method which handles all those problems and many others from geometry. There is a kind of algebraic tool which helps. So the next one is triple points on unit circles. So triple points. This one, well, it's not quite the number of distinct distances. This point is related to another famous problem of Erdős among n points. What is the maximum number of unit distances one can find? But this is a kind of very special case. Triple points of unit circles. So the first question is, question of Erdős. This is somehow the dual question. The question is that if you have n points on the plane, so n points in R2, then what is the maximum number of unit circles defined by this point set? A unit circle is defined by this point set if there are at least 3 points from that unit circle. Because otherwise, you have, of course, any 2 points might, if they are close enough, then they will give you a unit circle. But now, defining unit circle. So how many circles are there which have radius 1 and contain at least 3 points out of this point set. And the best construction is due to Elekes, so Erdős asked, probably conjectured, but I don't know, asked if the number of unit circles with at least 3 points, if this point set is P, at least 3 points from P is little n squared. So you can't have quadratically many such things. Please note that if you ask collinear triples, then of course if there are many constructions when you have C times n squared collinear triples, the densest construction would come from an elliptic curve with the right coefficients. But this is the question, and this is a beautiful open question. If you could prove, let me just mention, if you could prove that it can't be quadratic, that would also help to break the best known bound for the unit distances problem. The best construction is due to Elekes, where he defined a point set with at least n to the 3/2. With at least n to the 3/2 unit circles through the point set. Now, the problem which is related or relative to the other two is a restricted version of this one, of the dual. So let me erase this problem here. And let's ask the following, which was a question of Székely. So Székely's question is the following. We have 3 families of unit circles. We have 3 points and some set of unit circles, family of unit circles. One family goes through one point, the other family of unit circles goes through the other one, and the third family, well, they're supposed to have the same radius. So you have n unit circles here, n unit circles there, n unit circles there. And the question is that how many triple points will you see when an intersection point where one circle is from this family, the other circle is from that, how many triple intersections are there in this very restricted case? If you see in the dual, that's Erdős question, well, you can see the dual of the unit distance problem. Instead of the circles, you can take the centers, and instead of the centers, you can take the circle. So it's some kind of nice duality, but don't, for us, even if we just stay here, it's interesting. So here a much more general result is due to Elekes, Simonovic, and Szabó, where they proved something about triple points for families of curves. Actually, kind of one parameter family of curves. In this case, you see, to parameterize one of the circles through this point, you need just one parameter. What is the slope of the tangent in this point? That will uniquely define this circle. So those families are one parameter families. And in general, they have a much more general theorem. But again, they proved that, the maximum number of intersections, even just between two families, is not more than quadratic n squared. But the conjecture is that it's little o n squared, or even less, much less. They proved n to the 2 minus delta with a small delta, and that's with Raz, Orit Raz, Sharir, and myself. We proved and to the 11 over 6, which is much smaller than quadratic. So here is again, you see the exponents have something to do with each other, and it's really time now to talk about the methods. This is just here, we have 3 open problems. They are still open, and probably we are very far from the truth. One is distinct distances from 3 points. The second is the number of distinct distances should be large between 2 collinear set of points. And the third one somehow counts the number of accidents, or possible maximum number of possible accidents, when 3 circles go through the same point. You have 3 times n circles. What is the maximum number of triple? So, sorry, how much time do I have? Like almost 20 minutes. Then first, okay, let's see one example, maybe this one, the 2 lines. And first I will show you how to translate a problem like this into point curve incidences, where the point set is a very special one, a Cartesian product. That makes it easier to actually get incidence bounds. And then I will write down the general theorem, kind of algebraic following or extension or quantitative version of Elekes-Szabó and Elekes-Ronyai. But now our task is, again, here is this problem. We have 2 point sets, collinear point sets. How to bound the minimum number of incidences? Now I have to say that, well, you will see it at one point, but in Elekes-Szabó and Elekes-Ronyai, they used already kind of incidence bounds between points and curves, but they had complex curves, well, also complex, but higher degree curves, and they used the Bach-Charir bound. But if you really analyze those curves, I will show you one family, then you will see that they are almost like lines. And of course, for lines and points, we have better bounds, the so-called Semeridi-Trotter bound for incidences. But let's see the trick, how to translate the problem, this one, into problem of curves and lines. So, curves and points, incidences. First of all, just for the sake of simplicity, we can suppose that this is the origin and this is the x-axis, one of the lines. This angle here is alpha. Let's say if you have a point here, then the coordinate of the point above it, which has this x coordinate on the other line, is, say, some ni and s times ni. Okay, so everywhere you know it's the same x coordinate and then s times, so it's just the ratio. And let's see now 2 points here. Actually 4 points. 4 points such that the 2 distances are the same. So let's fix A and B. I fix 2 points in P1. This is P1. This is the set P1. And from P2, I'm interested about point pairs for this fixed A and B, where the distance to Q and P is the same. So this is a situation when the distance between A and P is the same as the distance between B and Q. And actually you will see that for the incidence bound, we will count such 4 tuples. And this is just Cauchy-Schwarz. If the total set of distinct distances is small, then you will find many quadruples when the distance from here to here and there to there is the same. If you won't find such configuration, then you are good already. There aren't many distinct distances. It's just a simple application of double counting, Cauchy-Schwarz. So let me define the curve which I'm going to work with, but this is kind of the key how. So let's define gamma AB. I fix A and B, and I define this curve. Well, gamma AB, this will be a hyperbola actually, where PQ, well, those will be variables, or rather their x coordinate will be in the zero set of this polynomial, of this hyperbola, if the distances are the same. So actually this is the simple equation what I'm going to write down, but for this special case. So let me write down ax squared minus bx squared. Let me write it down, and then, so that means that those are just the x coordinates of the points. Minus 2ax times x. Now x is a variable that will, so those are constant numbers so far. I just write down this distance, nothing else, plus, where are we? Plus 2bx y plus x squared times 1 plus s squared minus y squared times 1 plus s squared equals 0. So this is just to rewrite this distance equation. When are they equal? And those ax, maybe it's not a very good choice to choose the variable. This here a subscript x means that this is just the x coordinate of this point. It has nothing to do with the variable here. So those are just constant entries because I fixed a and b. And those are the unknowns, the variables, and this is a hyperbola, and this will give you, this is a curve, and this curve lives in P2 cross product P2. So this is the Cartesian product, where you know if you have 2 points which will satisfy this equation, then this curve will contain the corresponding 2 points from P2, right? So this is a kind of standard way in this whole business to write curves based on the problem. Well, it's kind of obvious, that's why I selected this one, because it's the distance polynomial. That's what we write down, and that's what we have here. Now, after that, what remains is to write down the incidence bound. You have to analyze it a bit. You can check that there aren't many intersections. If you have 2 points, then you don't have more than 2 curves going through. So you can apply the so-called Semeridi-Trotter incidence bound. Semeridi-Trotter incidence bound, which would give you the number of points to the 2. So Semeridi-Trotter, let's just write it down quickly. It's for points and lines, but it also works for points and pseudo lines, where you don't have too many intersections. It wouldn't work for circles in general. When you have 2 points and there are too many circles might go through, but if you have a bound how many curves can go through 2 points, then that works. So just very quickly, Semeridi-Trotter incidence bound, you have say n points and m pseudo lines. Then the number of incidences between the endpoints and m lines, if you wish, is the magnitude of n to the 2/3 times m to the 2/3, and you have to deal with the range when it's not very powerful, but that's not very interesting. This is just to deal with the trivial case. I won't go into the details here. This is, if you work with incidences, then this is something you know. If you don't, then we will do something slightly different in a minute. Good, but if you do the substitution and if you check just how many curves you have, so you have P1 squared such curves, because for every AB you have this. It's again a little bit of averaging or Cauchy-Schwarz to suppose that for most of the pairs they have at least the richness, the number of pairs what you would expect, and you just do the substitution and you get the bound which I promised, which is somewhere here, n to the 4/3. But because time is running fast, let me jump now and let me write down a very recent result. It's published on the archive, but this is the generalization of a sequence of theorems, and let's use that. That's the method I promised to prove the same bound. So what is it? First of all, who are the authors? So with Raz and Sharir, based on those observations, we extended Elekes and Rónyai. I will tell you what is this. I will tell you the general statement to give a quantitative bound there. And later on, they went further and they extended Elekes-Szabó and then even went to 4 dimensions. So let me state the following statement. Let me write, okay, this is mine. Let's do this. So this is a very recent result of Raz, Sharir, and the Zub. It's about a polynomial, so let me write down the statement. Let's F be a complex polynomial. Well, for most of the applications, we work with reals, but doesn't matter. So of 4 variables, so it's a 4-variable polynomial. And let us suppose that this is irreducible. And degree D, this is fixed. We fix the degree. We think it as a constant. Somehow the hidden constant will depend on D. And now there are 2 cases. One is that no matter how we choose, well, a 4-dimensional set, so there are 2 cases. Let me, before I write it formally, let me tell you what are the 2 cases. You have this polynomial of 4 variables. Either this polynomial has small intersection of any 4-dimensional Cartesian product, A, B, C, D. So not integers, nothing. It's just a Cartesian product. Cartesian product is a structure. Either your polynomial has a small intersection. Well, suppose that you have the same size A, B, C, D sets, and you intersect with the Cartesian product, C and D, and they all have the same size. Of course, they have the general theorem, but for us, it's enough to see what's happening when they all have n. So either the maximum number of intersections, well, what would be the maximum? It would be n cubed. If you have, say, 1 slice, that would be n cubed. Now, either your polynomial has intersection much less, it's 2, 4, 6, 8, 8/3. Sorry. So 2 cases. You have this, you check the 0 set of this polynomial, so the 0 set of this polynomial intersection with this one. It's either smaller or equal than n to the 8/3, definitely smaller than 8 cubed, well, than n cubed, sorry, n to the 8/3, or it has a very special structure. It's a very special polynomial. And in most of the applications, you can show that, no, it's not that special. So the special thing is that locally, at least in the neighborhood, well, you remove a 0, well, some lower dimensional subset, but don't worry about that. This is just technical detail. But in most of the places, this is one case, and the other case, and then you get the bounds what you need. In the other case, well, it's only possible if f is locally. That means that you have a so take a point of this surface, f equals 0, that's a surface. Take a point, and you take then you can find a subset and a small cube, And in this cube, f is 0 if and only if. So in this cube, there are analytic functions phi 1, phi 2, phi 3, and phi 4 that f in this neighborhood locally, fxy, what did I use, st, equals 0 if and only if phi x plus phi 1x plus phi 2y plus phi 3s plus phi 4t is 0. So locally you can write it as a sum of analytic functions which only depend on one variable. I don't care what kind of analytic, well, you will find in examples when those analytic functions are ugly. But immediately you see that the mixed partial derivatives, the second mixed partial derivatives should be 0, if, at least locally, if you have this form. And now you can check what's going on. And this is my last example to prove the very same theorem, but using this. So as it went in 3 dimensions, there were some theorems, but this is the most recent one in dimension 4. And let's just use this one to prove this bound, to use it without incidences. Actually, I have to tell you that when you prove such theorem, then locally you go through in an abstract way on such incidence bounds. So this is still a good hint how to prove that theorem. But let's just see an application of this theorem. So if you have 4 points, let's just keep like this, and you count how many times you have the same distance between 2 points. So here is 1 point, another point. This is alpha. So you know that this distance here, say AB, what was that? QP. I will count the number of pairs of distances which are the same. And again, it's just a simple Cauchy-Schwarz to get back the real bound. So let me just bound the number of pairs. So if the distance set is, say, D, then altogether you have n squared possible pairs. N squared over D, that's the typical number of pairs you have for one particular distance. Let's just see the average, yes. You have n squared possible pairs and D distinct distances. Then n squared over D will be the number of pairs in one distance set, typically. And I count the pairs, so the square, and for every distance set, I count that. So this is the number of pairs I will find, at least. Right? On the other hand, let's write down this. So this is, let's just write down. I can also parameterize with the length. It's L1. Here it's L2, L3, L4. Anyways, just it's L1 squared plus L3 squared minus 2 L1 L3. It's just the usual counting for times cosine alpha. This is the length here. This is the same as L2 squared for such pairs plus L4 square minus 2 L2 L4 cosine alpha. Yes, that's what we count. We count this is the polynomial, and we are interested about the zero set of this polynomial, and it will vanish on the distance set. Well, the square of the distance is set. Well, one more dimension, but I don't have to draw it. And there are two cases. Either either this has a small intersection, and then the number of solutions is smaller than 8 over 3, but we counted the pairs, the square, so that would be 4 over 3. Or it has a special form. And what are the special forms? So, first of all, I assumed in the theorem that this is irreducible. But it's not irreducible if it's orthogonal, because you can write it as a product, right? You see? So if this part is 0, then you just have nice difference of squares and you write it as a product. So it was not irreducible. It won't work and it shouldn't work when they are orthogonal. And the other case is, what happens if they are parallel? Then you get back exactly this case. Just a function of x, y, z, yeah, because there's no mixed term. And for every other case, if you see the second mixed derivatives, they are not 0. So the only remaining part is, indeed, the number of distinct distances is at least n to the 4th third. So thank you very much for your attention.